Okay, besides calculation, let's examine some material property on the gas and its influence on its gas spectrum. So this is the full expression for the gas spectrum here. So let's see what might change the gas spectrum. First, if I use the material with a larger effective mass, a material with larger effective mass, for example, gallium nitride, aluminum nitride, those wide bandgap materials that require high effective mass of electron in the hole. So a higher effective mass will give you a higher reduced density of state. So the G mass will enhance. Since you have so many pairs, so that will give you a potential engine to providing gain. But however, since you have so many states near the band edge, it is more difficult to make the Fermi levels separate. Since you need to remove plenty of electrons from valence band to the conduction band. So a higher effective mass of material will reduce F2 minus F1 under the same pumping. That means this material is more difficult to pump, more difficult to achieve population inversion. But if you can achieve population inversion, it gives you a higher potential to give you a higher gain. Okay, so that's a very major difference between the free nitride material and the other group, either gallium arsenide GaAs based or IMP based materials. Second, what might we do with the material dimension? For example, it's bulk, it's quantum well, nano wide, or quantum dot. For the Gmax, it generally reduced because the lower DOS. Since it reduces its dimension, it's reducing its density of space. But we already observed that it might still enhance because you will changing the transition matrix error. So it is selective. So it doesn't have a direct conclusion. That will depend on the polarization of your light and how your conduction band change with different dimension. So it's not definite. It could be make a Gmax higher or Gmax lower. That it depends on your design. So there will be lots of work to do here. But for F2 or F1, the answer is easy. Because you reduce the density of state, now you have less electron at the edge and less electron at the band edge at both sides, so it's easier to pump your material to population inversion. So quantum wave laser will definitely have a lower threshold than DH laser. A nano wire or quantum dot laser will even have a lower threshold for population inversion. That depends on do you design your structure right. But generally, in a higher perspective of the material, that will definitely make your material easier to lace. What about use the wide bandgap material? Since the first it has a larger effective mass. However, wide bandgap material has other properties. First, since you have wide bandgap material, you have a higher F1 for sure, but you also have a higher reduced density of state. So it might be competing each other. At least for gallium nitride and the gallium arsenide, the higher density, the influence of density of state prevail. Okay, and about the compressive strength of the material, it will reduce because while you have a material you have a compressive strength of your material, your heavy hull and the light hull split. This is heavy hull. This is light hull. This is unstrength. However, if you put it by a substrate with a smaller lattice constant, you compress it. So that will make it like a heavy hull. Light hull, something like that. Okay, then this is the easy. So at the bend edge, for the unconstrained case, the density of state in the heavy hull and the light hull all counts. But while it split due to the strength, these two differentiate. So at least for transition between your heavy hull the transition between the bend edge, between the conduction band and the valence band edge, there's only one band counts. So the density of state reduced a lot. Less density of state at the band edge means a higher F2 minus F1. It's easier to make the Fermi level separate that high. So a compressive strength isn't a bad thing if you can grow it. If you grow a compressive field and you cannot keep it for 3 nanometers, that means you can even put a high quality field. That is a bad thing because everything is good. However, if you can grow a field with a compressive strength, from this point of view, it is actually benefit for reducing your threshold current density, carrier density. So that would be a competition. A compressive field will ruin your material property. But a compressive field also split your heavy hull and light hull. That's a pretty technical or pretty engineering argument. Then how good can you grow your compressive field? So that become the real issue. It's nothing about science anymore. It's about technology. Okay. There's also for gallium nitride, there's something called the internal electric field. Yeah, if you take Professor Science physics, we call it the internal polarization. Internal polarization field that we didn't introduce in this class, but that will change the energy band directly. That will make the F2 and the F1, the wave function overall being reduced. It's actually not good for Gmax. So there's a lot of people trying to work with that to grow the material with different direction. That's also a very interesting story. I got my PhD doing things about this, but that will be not what you need to learn now. Just leave here. Okay, so you see this is some good paper about the benchmark of laser different activity. At the early days, we do the DH laser. And the GAS PN junction DH laser, it is bad. The threshold current density is super high. It's so high that you cannot measure that. But as the material technology improves, yeah, indeed improve little by little, but it has some limitation here. Then we change to the quantum wave structure for the SPH structure. At the beginning, the result looks bad. It's disappointing. Yeah, you even make a device worse than the previous publication. But that's because while you're doing something new, you have lots of new technology issues you never encountered. But if you have the right theory and trying to improve that little by little, yeah, eventually they'll make the threshold carrier density one order lower than the original DH structure. Then also quantum dot, yeah, you can see it's even a further one order lower for the threshold carrier density. Yeah, that's all because reduced dimension has reduced the density of state. The reason is simple, but you take a UC from 1960, 2000, yeah, it's a topic people can do 40 years with the same material. So semiconductor laser is a good topic for everyone to do for quite a while. Okay, this is gallium nitride. It has some important property with the commonly known gallium arsenide and the major difference is the crystal structure has a low symmetry. For gallium arsenide and IMP, the XYZ direction are all equal. So there's no spatial axis for GS IMP. But for gallium nitride, there is important that the direction of 001 differ from the other. So it has symmetry called preference, but that's just a name. Anyway, the C axis is giving it breaks the symmetry, so the positive aluminum of the negative ions has a polarization along the C axis. So while you're drawing your band structure, because the polarization is different. So the Gauss's law, that the divergence of P is equal to H1 over charge density. Since the polarization of one to the other, for example, an aluminum gallium nitride and the gallium nitride has different P. So delta P at its interface is an infinite value. So it has a delta function at its interface. Such delta function at both interface make the band diagram or band structure a serrated structure. Serrated, that means it's just like a saw, the edge of saw, 像锯子一样，高高低低，高高低低。So this kind of polarization makes a new concept only in free diagram material called the confinement stock effect. That means at the low injection, because the shape of the band structure is not symmetric. It has a low, high, low, high. So that will make the injection, the carrier wave function tilted for electron at one side, but tilted for hole for the other side. So that will make the so-called F1, F2, the wave function order pair reduces. So it becomes a core topic of the InGaN LEDs for around 10 years or 20 years. But fortunately, while under the high injection, the newly injected carrier will split the carriers at the boundary. So it will still eventually flatten. So the transition wavelengths at the beginning it will be short. But at high injection, because the band structure flattens, so it causes a very significant bullshit. The distance between the cross states will be enlarged because the band diagram becomes symmetric after injection. So that will give you a very significant shift of your EL and the GaN spectrum with carrier. So this also makes the gallium nitride a difficult material to make lasers. But fortunately, now as long as the quality is good enough, this should be no a problem now. Yeah, that this makes you very ultra low threshold very difficult. Unlike the gallium arsenide with a very low threshold current density, as long as the material is good and the design is correct, that will make you makes the lasing still possible. But for gallium nitride, if the injection current density is high, the overlapping function is small. It's still difficult to make an ultra low threshold. But so in this case, you need a new story to either to combine the electron or combine the light. So it's still a growing field. Yeah. But the issue is few people can really get out of gallium nitride material.